Hi students, good morning all of you. Welcome to my channel Arjun Reddy IIT NEET Foundations. From long back, I am planning to start my YouTube channel. Finally, I started, right? So from today onwards, I am trying to upload videos on maths, physics and chemistry. Actually here, my target is not 2026 mains. My target is 2026 April mains and 2026 advanced. Okay, so before that I will try to complete my total syllabus from maths, physics and chemistry, right? So without wasting your time, today I am going to discuss about isomerism. Now we know that organic chemistry point of view, now two important basic concepts are there, like general organic chemistry and isomerism, right? So these two are what very important to understand the remaining organic chemistry. Even few questions we are expecting from general organic chemistry and isomerism. Okay, why? Because in most of the cases, now once we observe either in mains or advanced, right? So for example, if they are giving what question, they are connecting some isomerism related questions are there, even though that is the normal question, but they are connecting some isomerism part. So like that, in case of organic mechanism and if for example, if you want to explain the acidity, basicity and stability of intermediates, you require general organic chemistry, right? So that's why organic chemistry point of view, now these are the two basic concepts, general organic chemistry and isomerism, right? In this first video lecture, we are going to start with isomerism, right? Now first basically, now before going toward different types of isomerism like structural isomerism, geometrical, optical and conformational isomerism, what is the fundamental definition for isomerism and what are the requirement conditions for isomerism, that I want to discuss here, right? Now to define isomerism, our first topic is what isomerism. To define that isomerism, once again I want my empty page, right? Yeah, so I'm going to define first isomerism. How we are defining that isomerism? Okay, so to define isomerism and isomers, I am taking two fundamental examples, very well known examples, very simple molecules, CH3 CH2OH, ethyl alcohol, and dimethyl ether CH3OCH3. One is alcohol and one is a dimethyl ether. I am going to compare boiling points of this alcohol and ether. So boiling points here around 76 degrees centigrade. Here boiling point is how much? Around 17 degree centigrade. Okay. Whether these are what exact values or not, but around 76 degrees centigrade and here 17 degrees centigrade, right? So why boiling point of alcohol is more when compared to what ether? What is the reason? Now we know that OH functional group is present in alcohols that can develop hydrogen bonds, but in this one there is no hydrogen atom on the oxygen atom, it cannot develop hydrogen bond. That's why, because of hydrogen bond strength, alcohol molecules boiling point is more when compared to what ethers. These are less volatile compounds and these are more volatile compounds. What is the reason for volatile nature? Based on boiling point, its boiling point is more and its boiling point is less. Ethers are more volatile when compared to what alcohols. Now this is the physical property, boiling point, right? Boiling point of alcohol is more when compared to what ether. Now let us compare second property in terms of what chemical property, right? Ethyl alcohol CH3CH2OH plus sodium. What is the product? Here you are getting ethoxide ion CH3CH2O minus Na plus half H2 gas, and for example same reaction if you are doing with dimethyl ether with sodium, there is no reaction. Okay, before going to define that isomerism term, just you understand these two properties. What is the first one? Boiling point, they are having different boiling points, and the second one molecule giving reaction with sodium and second molecule not giving reaction with sodium. That means they are showing different chemical properties. Now we will define isomerism, right? Here, what is the common feature of these two molecules? How many carbon atoms present? Yes, 2 carbon atoms are there. And how many hydrogen atoms present? Yes, 6 hydrogen atoms are there and 1 oxygen atom, right? C2H6O. Molecular formula same or different? Yes, they are having same molecular formula. Once molecular formula same, by default, what about the molecular weight? Yes, molecular weight also same. Once same is the molecular formula, by default degree of unsaturation also same, right? Why? Because that is a very important condition for isomerism. Now molecules are having what? Same molecular formula, but what about the physical properties? Different, and here chemical properties are different. Okay, so on the basis of these properties we can define isomerism. Isomerism. What is the fundamental definition for isomerism? Molecules having same molecular formula. MF nothing but molecular formula. Molecules having same molecular formula and at least they can show, or they will show at least they differ in one property, or once again molecules are having same molecular formula and at least they will show one different property. Then the molecules are said to be isomers. Then molecules are known as isomers. Molecules are known as isomers. That is the fundamental definition. Sir, what is the property here? So any property you can use in terms of physical property, in terms of chemical property, or in terms of optical rotation. So whatever the property, at least now they differ in one property. So once again, molecules having same molecular formula and at least they will show one different property, then molecules are known as isomers and the phenomenon is known as isomerism. That is the fundamental definition for isomerism. Fine. Now, what are the different types of isomerism? Different types of isomerism on the basis of what? Connectivity, right? Isomerism. Basically here we have two different types of isomerism. What is first one? Structural isomerism. Yes, structural isomerism. And what is second one? Stereoisomerism, right? Structural isomerism and stereoisomerism. That is the basic classification of isomerism. Sir, how we are classifying that structural isomerism and stereoisomerism? On what basis we are separating structural and stereoisomerism? Yes, very easy to understand. Here I am taking one simple example, that alcohol. In the first alcohol I am taking with 4 carbon atoms and OH is present on this carbon atom. Yes, in the second molecule same OH I am connecting here. In the third molecule this is my OH connectivity. These are the 3 molecules. Once again you observe what is the common feature of these molecules. What is the common feature? Same molecular formula. I am not changing molecular formula. Okay, same is the molecular formula, right? This is very important condition. Either in structural isomerism or stereoisomerism, molecules should be with the same molecular formula, right? Now just you look at the connectivities. Otherwise, now same molecules I am taking here, but in this one I am taking one OH on above the plane. We know that if you are using thick wedge, that indicates above the plane. In the second molecule, same OH I am taking below the plane. With the same molecular formula, here OH I am taking below the plane. Now you observe the difference, basic difference between these molecules. Here are molecules, molecular formula same or different? Yes, molecular formula exactly same. But in first molecule, your OH is present on which carbon atom? 1 degree carbon. Here OH is present on which carbon atom? Yes, 2 degree carbon atom. Here OH is present on 3 degree carbon atom. That's the difference. Yes, molecular formula exactly same. But where we observe the difference? Connectivities are different. Connectivity is not same. Connectivities are different. OH on primary carbon, OH on secondary carbon, and OH on tertiary carbon atom. 3 degree carbon. Now come to these molecules. Molecular formula same or different? Yes, molecular formula same. And connectivity is also same. OH connected with the secondary carbon atom. Here also OH connected with secondary carbon atom, 2 degree carbon atom. But what is the difference? In first molecule, Your OH is connected above the plane. Connected above the plane, fine. And here OH is connected below the plane. That's the difference. Same molecular formula, same is the connectivity, but what is the difference? Spatial arrangement is different. Okay, space geometry is different. One is above the plane, one is below the plane. That is the basic difference between structural isomerism and stereoisomerism. In structural isomerism, once again, in structural isomerism, same point I am writing here, they are having same molecular formula, but connectivity is different. Connectivity is different. This type of molecules we will study under constitutional isomerism or structural isomerism. So they are giving question like this, sometimes structural isomerism or sometimes constitutional isomerism, both one are same. Once again, structural isomerism or constitutional isomerism. What is the condition in structural isomerism? Molecules are having same molecular formula but connectivities are different. Okay, right. Next, in these molecules, now same molecular formula, these are having same molecular formula but spatial arrangement is different, space geometry is different. Those molecules comes under what? Stereoisomerism. Okay, that is the basic classification of isomerism in terms of structural isomerism and stereoisomerism, or constitutional isomerism and stereoisomerism. Okay. Yeah, next one, different types of isomerism. Here I am going to write different types of isomerism. Yes, I want next page. Yeah. Once again, structural isomerism. Yes. Second one, stereoisomerism. Right. In structural isomerism, what are the different types? Yes. First one, here I am writing like this. Chain isomerism. Yes. Chain isomerism. Second one, ring chain isomerism. Third one, positional isomerism. And fourth one, metamerism. Fifth one, functional isomerism. Yes, functional isomerism. And sixth one, tatamerism. Okay, fine. These are the 6 different types of structural isomerism or constitutional isomerism. Now here in the first phase we are trying to cover up to functional isomerism, and I am going to make separate video on tatamerism. Why? Because that is a little lengthy topic when compared to what now individual structural isomerism. Right? Ring chain isomerism, positional isomerism, metamerism, functional isomerism, and tatamerism. And what about the stereoisomerism? Stereoisomerism, 2 types. First one, configurational isomerism. Yes, configurational isomerism. Second one, conformational isomerism. Really, these are very beautiful concepts. Configurational isomerism and conformational isomerism. Yes, configuration, again 2 types. One is what? Geometrical isomerism, and second one, optical isomerism. Yes, optical isomerism. Okay, these are the different parts of isomerism. So once again, isomerism 2 types: structural isomerism or constitutional isomerism, and what is the second part? Stereoisomerism. Structural isomerism, again how many types? Chain, ring chain, positional, metamerism, functional isomerism, and tatamerism. Stereoisomerism, how many types? Configurational isomerism, conformational isomerism. Again configurational isomerism, how many types? 2 types. geometrical isomerism and optical isomerism. Yes. Now directly we are going for chain isomerism. Let me start with chain isomerism. Chain isomerism. Yes. Chain isomerism. Okay. So one by one we will discuss in chain isomerism what is the first important condition. First important condition, molecules should be with the same molecular formula, or simply I am writing like this, molecular formula same. MF nothing but molecular formula. In short form I am writing like this, molecular formula same. And what is the second and very important condition to classify the given molecules into chain isomers? Okay. Now chain means we have two chains, side chain and parent chain. First look, we are looking for parent chain. Parent chain length should be different. Parent chain length should be different, or size of the parent chain should be different. For example, if parent chain is same, then we go for side chain, or otherwise just you remember like this. No need of this point, so directly I am writing like this. So we have parent chain, yes, parent chain, and second one side chain. Okay, right. First you look at parent chain. For example, parent chain is same, then go for side chain. For example, parent chain is different. Yes, they are classified under chain isomers, and sometimes parent chain is same, but length of the side chain is different. Size of the side chain is different. Then also we can classify them into chain isomers. Okay, these are the two conditions. So once again, for any molecules, now we are discussing under isomerism. What is the first important condition? Molecular formula should be same. And in case of chain isomerism, we are looking for parent chain. If parent chain length is different, then the molecules are said to be chain isomers. And sometimes size of the parent chain is same, then go for side chain. If size of the side chain is different, then the molecules are classified under chain isomers. And another important one, we are not changing the functional groups. Why? Because if functional groups are different, then the molecules goes into functional isomerism. Now again I am writing same points. Functional group, FG nothing but functional group. Functional group should be same. This is a very important point. Same functional group we are maintaining, right? Let us start examples for chain isomerism. For example, if I am starting with methane, CH3 and CH3, ethane, CH3, CH2 and CH3. Now propane and butane molecule. Okay, otherwise first let me complete these three molecules. With these three molecules, is there any chain isomerism? Here chain isomerism is completely absent. There is no chance to produce chain isomers by using methane, ethane and propane. For example, if you start from 4 carbon atoms, yes, how many carbon atoms are there in the parent chain? 1, 2, 3, 4 carbon atoms. And same molecule, just I am writing like this with 3 carbon atoms. And what about the 4th carbon atom? Now 4th carbon atom I am correcting here. Now just you can select the parent chain first, 1, 2, 3 and 4. How many carbon atoms present? 4. But here 1, 2 and 3 carbon atoms only. Only 3 carbon atoms are there in the parent chain. Then once size of the parent chain is different, what is the relation between these two molecules? These two are chain isomers. That's it. Very basic example. Chain isomers. Yes, I am going to take with 5 carbon atoms, 1, 2, 3, 4, 5. And how to produce chain isomers? Nothing is there, just you select length of the carbon chain with 4 carbon atoms and 5th carbon atom I am connecting here, but not here. For example, if you are connecting here, again you will get same molecule. Not only here, even you can do like this, 5 carbon atoms and 5 carbon atoms. Now you select the number of carbon atoms in the parent chain, 1, 2, 3, 4 and 5. Yes, here 1, 2, 3 and 4. Only 4 carbon atoms are there. Length is different. These two are said to be chain isomers. Yes, very clear. Come to next example. 1, 2, 3, 4, 5. 1, 2 and 3. Same molecular formula, but length of the parent chain is different. Again, these molecules classified under chain isomers. Write down these examples. Yes, clear? One second, let me check my video. Yeah, clear, no problem. Yes, I am going to take unsaturated hydrocarbons like alkenes. I am trying chain isomerism with alkenes like this. Yes, 4 carbon atoms. Here I am taking 3 carbon atoms and this is the methyl group. Next one. Here, for example, 5 carbon atoms are there, and here I am taking 5 carbon atoms and 1 methyl here. Even you can use like this alkane and double bond. Here we can write the methyl group. Here how many carbon atoms present in the parent chain? Now just you count from double bonded carbons. 1, 2, 3, 4. Here 1, 2, 3. Bus. 1, 2, 3, 4 carbon atoms, but in the second molecule 1, 2, 3. What is the relation between these two? Once again, chain isomers. We are not changing the molecular formula and we are not changing degree of unsaturation. Only length of the parent chain is different. Right. Here 1, 2, 3, 4 and 5. What happened to this one? Yeah. 1, 2, 3, 4 and 5. 1, 2, 3, 4, 5. Yes. One second. Where I am doing mistake? Let 4 carbons bus. Yeah, set हो गया. One second. Let me write one. Same molecule with, oh shit. Yeah, with 4 carbons I am taking like this, and somewhere I am writing methyl group. Yeah, this is my molecule. Here 1, 2, 3 and 4. Clear. Again these two are what? Chain isomers. And come to this example. 1, 2, 3, 4 and 5. Yes, but here 1, 2, 3, 4 and 5. Okay, same molecule I repeated. Please remove this example. Yes, these are the chain isomers, right? And let us try with some functional groups. For example, if you are taking like carboxylic acids, 2, 3, C double bond OH, and here I am taking like this C double bond OH, and somewhere I am writing methyl group. Here how many carbon atoms present in the first molecule? Yes, 1, 2, 3, 4, 5. Here 1, 2, 3, 4. That is the parent chain. So your parent chain is different with the same functional group. What are the types of isomers? These are chain isomers. Okay, right. Now let us come to another example. Sometimes they are giving like this. With 3 carbon atoms I am taking. Here I am taking Cn. Again here also Cn. I am changing position of Cn like this. Cn, again Cn. They are looking like positional isomers. Don't get confusion. They are looking like positional isomers, but they are not positional isomers. Why? Because what is the way of giving numbering in first molecule? 1, 2 and 3. But here 1, 2, 3 and 4. Molecular formula same. Same molecular formula, but length of the parent chain is different. For example, if you have any doubt, just you count the number of carbon atoms. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Now these molecules classified under chain isomers. These are also classified under chain isomers. Very simple examples, right? Let me go to another example here. For example, unsaturated systems are given like this. Yes, double bond here, another double bond is here for chain isomers. Yes, and in the second molecule like this. Okay, fine. What is the relation between these two? First, to identify the relation, yes, molecular formula same. I am taking same molecular formula. How to give numbering in the first molecule? So according to IUPAC, first maximum number of double bonds we are trying to bring into the parent chain. Right, you start from here. 1, 2, 3 and 4. And here 1, 2, 3, 4, 5, 6. So if you have any confusion, clearly again I will make the perfect video on IUPAC nomenclature. There you will get idea how to give the numbering for a given molecule. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Parent chain is different. Length of the parent chain is different. And what is the relation between these two chain isomers? Clear. Okay, chain isomers. And I am giving some very important examples, cyclic compounds. From cyclic compounds, for example, like this cyclohexane ring system and cyclopentane ring system, outside one methyl group. These are also very important. Cyclohexane ring system, here I am taking like this 4-member ring system, outside ethyl group is there. Okay, and for example, if you are taking like this, yes, methyl and methyl, and here 3-member ring system, outside methyl, 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 any type of combination they can give. And even sometimes, for example, like this and second molecule is cyclohexane. What is the relation in the given pairs? How many carbon atoms in the parent chain? 6 carbon atoms are there. But in the parent chain, how many carbons present? 1, 2, 3, 4, 5 carbons only. Why? Because here cyclic system is the parent chain. Here how many carbons present? 1, 2, 3, 4, 5 and 6. Okay. Now these two are classified under chain isomers. Very clear. Next one. In the second pair, how many carbons present in the parent chain? 1, 2, 3, 4, 5, 6. Next, 1, 2, 3, 4 only. Molecular formula same, but parent chain size is different. Again, these are what type of isomers? Chain isomers. Yes, come to next example. Here 1, 2, 3 and 4. Here 1, 2 and 3. What are the types of isomers? Yes, chain isomers. Next one, 1, 2, 3. We know that whenever cyclic compound is given and outside the ring some substitution is present, right? Here, up to equal number of carbon atoms, our cyclic compound is the parent chain. That I will discuss in IUPAC nomenclature. Here count number of carbon atoms 1, 2, 3, 4, 5, 6. What is the relation? Same molecular formula, but parent chain size is different. These are also classified under chain isomers. For example, if question is given like this, on the basis of side chain I am giving, for example, 4-member ring system and outside the ring system ethyl group is there. Next one here, 4-member ring system, methyl and methyl. What is the relation between these two? First we are looking towards parent chain. Here 1, 2, 3, 4. Here also same thing, 1, 2, 3, 4. Parent chain same or different? Yes, parent chain is same. But where we observe the difference? In first molecule, what is the side chain? Side chain is ethyl. In the second one, what is the side chain? Methyl, methyl. Methyl, methyl. Same or different? They are different. So once side chain is different, then also we can classify them into chain isomers. Very important. These examples I am giving on the basis of side chain. Let me give one more example just to avoid confusion. Right here, aromatic ring system I am taking, outside the ring system ethyl. Here aromatic ring system methyl and methyl. What is the relation between these two? They are not positional isomers. Why? Because in case of positional isomerism, only positions are different but same parent chain length and same side chain length. But in case of chain isomerism, this is our parent chain, here also same parent chain. But what is the side chain? Ethyl. Here what is the side chain? Methyl, methyl. So once the side chain is different, then these are also classified under chain isomers. Okay, this is the story about chain isomerism, right? Next one, positional isomerism. Let me explain about positional isomerism. Positional isomerism. Yeah, fine. How we are classifying the molecules in terms of positional isomerism? First point, same molecular formula. Second one, same functional group. Same functional group. I think I am forgetting ring chain isomerism. Okay, no problem. After positional isomerism, we will discuss about the ring chain isomerism. Okay. Here under positional isomerism, same molecular formula, same functional group. Why we are writing particularly same functional group? According to the priority order, if functional groups are different, we are neglecting chain isomerism, positional isomerism and metamerism. That's why we should maintain same functional group. Same molecular formula, same functional group. But on the basis of this one, position of substituents are different. Okay, on the basis of this one, we are classifying the given molecules into positional isomerism. So same molecular formula, same functional group. Next, what is the third point? Position of substituents are different. We are not changing side chain. One second, I am writing these 2 points also. Remember, in positional isomerism, size of side chain same. Okay, second one, size of parent chain also same. Size of parent chain also same. Remember these 2 points. In positional isomerism, size of side chain is same and size of parent chain also same. Yeah. So I am going to give examples for positional isomerism. Yes. In positional isomerism, in case of normal saturated hydrocarbons like methane, CH3CH3 and CH3CH2CH3, even N-butane molecule, N-pentane molecule, with these molecules there is no positional isomerism. No positional isomerism. First important point. Maybe sometimes theoretical questions they are asking, which of the following molecules does not shows positional isomerism? Now with these molecules there is no chance to produce positional isomers. To produce positional isomers, minimum we require 6 carbon atoms. Out of 6 carbon atoms, I am taking 5 carbon atoms like this. Here also same thing, 1, 2, 3, 4 and 5 carbon atoms. First minimum I am starting with 6 carbon atoms. Out of 6 carbon atoms, 5 carbon atoms I am writing like this. Next one, CH3 and CH3. Okay. In the first molecule and second molecule, what about the parent chain? Parent chain exactly same. And side chain length, again side chain length is same. Who is the side chain? Methyl. Here if you are giving numbering like 1, 2, 3, 4 and 5. Here 1, 2, 3, 4 and 5. What is the position of your methyl in first molecule? That is present at second position, and here say methyl is present at third position. Okay, that's why these 2 are what said to be positional isomers. Very important. In positional isomerism, we are not changing length of the parent chain and length of the side chain. But what is the difference? Only position of substituent is different. Not only simple methyl groups and ethyl groups, sometimes we are taking like this functional groups like OH and NO2, but without carbon containing functional groups. Yeah, no problem. No need to remember every point. Just by looking at the molecule, we can separate them in terms of positional isomerism. Yes, here I am taking OH, right. In the next molecule, here I am taking NO2. Here, same thing like NO2. For example, if you are taking unsaturated systems like this, again position of double bond, here triple bond, position of triple bond like that. For example, if I are trying with any kind of functional group and somewhere I am taking like chlorine atom, right, and here same carboxylic acid OH, and this is the position of chlorine atom like that. Okay, any type of example. Now come to the second pair. Here OH is present on which carbon atom? First carbon atom. Here same OH is present on which carbon atom? Second carbon atom. What is the relation between these two? Positional isomers. Okay. Why? Because here parent chain is exactly same. Just we are changing position of OH. And come to this molecule 1, 2, 3, 4 and 5. Next one 1, 2, 3, 4, 5. What is the position of N-BO2? Second position, and position of N-BO2 third position. What is relation between these two? Yes, positional isomers. Next one 1, 2, 3, 4. 1, 2, 3, 4. What is the position of double bond? In the first molecule, position of double bond is at first position, that is a locate, and in the second molecule, second position. So these two are comes under positional isomers. Like that, next pair also comes under positional isomers. And what about this one? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Chlorine atom position is different. These are said to be positional isomers. Okay, fine. Clear? I am giving some examples from aromatic ring systems. Those are also very important. I am trying with dichlorobenzene, dibromobenzene, anything. Dichlorobenzene is given. How to arrange chlorine atoms here? Chlorine and chlorine 1, 2 position, and same chlorine atoms I am taking at 1, 3 position. Even you can arrange at 1, 4 position, chlorine and chlorine. Clear? How many isomers are there? Total 3 positional isomers. Number of positional isomers equals to 3. Sometimes they are asking number also along with now relation between the molecules. Yes, clear? For example, if I am taking trichlorobenzene, trichlorobenzene. First one dichlorobenzene is given. Next one trichlorobenzene. Yes, chlorine, chlorine and chlorine. Trichlorobenzene. What are the possible positional isomers of trichlorobenzene? Yes, we can write like this. And what is the second possibility? Chlorine, chlorine and chlorine. Third possibility, chlorine. Yes, chlorine, chlorine. What are the number of positional isomers? Yes, number of positional isomers equals to 3. Okay, first one dichlorobenzene, second one trichlorobenzene. Come to next example. Yes, I am trying with the tetrachlorobenzene. Yes, 4 chlorine atoms I am taking. There is no specific formula to calculate these positional isomers. Just you try to find out by changing the position of atoms, like tetrachlorobenzene, chlorine, chlorine and chlorine. This is my first molecule. Yes, second molecule, chlorine, chlorine, chlorine. I can arrange chlorine here. That is the second possible structure. And what is the third possible structure? Chlorine, chlorine, chlorine and chlorine. These are the maximum possibilities. What are the number of positional isomers? Number of positional isomers equals to again 3. Okay, fine. For example, cyclohexane ring system is given like this. Cyclohexane, methyl and methyl is given. In the question, simply they are giving dimethyl cyclohexane. Dimethyl cyclohexane. What are the possible positional isomers of dimethyl cyclohexane? Clear? This is my first possibility, 1, 1 dimethyl cyclohexane, or you can write like this 1, 2 dimethyl cyclohexane, or 1, 3 dimethyl cyclohexane. Even you can write like this 1, 4 dimethyl cyclohexane. These are the possible positional isomers. Number of positional isomers equals to 4. Number of positional isomers equals to 4. Okay. Very good example, dimethyl cyclohexane. First one, 1, 1 dimethyl cyclohexane. 1,2-dimethyl cyclohexane, 1,3-dimethyl and 1,4-dimethyl cyclohexane. Clear? Right. One more question I am giving, that under positional isomerism, what are the possible positional isomers of trichloropropane? Right? Possible positional isomers of trichloropropane. Yes, very good question. Just try this example. Trichloropropane. Number of possible positional isomers of trichloropropane. Now here I am taking trichloropropane. First I am writing propane skeleton, right? Yes. How to arrange the chlorine atoms? First here I am giving one chlorine atom to each carbon atom. That is the first possibility. Next I am trying with the two chlorine atoms. Here 2 chlorine, here 1 chlorine, right? Here 2 chlorine atoms, at the last carbon atom 1 chlorine. Otherwise 2 chlorine atoms if you are giving to, yes, middle carbon atom and other chlorine either right side or left side. And what is the last possibility? 3 chlorine atoms are given to same carbon atom. These are the possible positional isomers. Now here number of positional isomers equals to 5. Very good question. Number of possible positional isomers equals to 5. Yes, clear? One more question, that is possible positional isomers of tetrachlorocyclobutane. What are the possible positional isomers of tetrachlorocyclobutane? Yes, this is my cyclobutane ring. 4 carbon atoms are there in the ring. Yes. And I am trying to arrange chlorines, 4 chlorines. First I am giving chlorine and chlorine. Each carbon 1 chlorine atom. Okay. In the second one I am giving 2 chlorine atoms like this. Chlorine and chlorine, and the next carbon atom chlorine. And I am changing the position like this, chlorine. Again here chlorine and chlorine, right? Another possibility, chlorine and chlorine. Here chlorine and chlorine. Last one, chlorine. 1 chlorine here, another chlorine here. These are the possibilities, right? Even you can verify. Also no problem. Here number of positional isomers equals to 5. What happened to this? No problem. Number of positional isomers equals to 5. Okay. I am giving one question on positional isomerism, right? Write all possible positional isomers of dichloro-naphthalene. Okay, very good question. Write all possible positional isomers of dichloro-naphthalene. Okay, right. So how to write all these possible positional isomers? I am going to write first naphthalene. I am taking naphthalene rings. After that I will try to arrange chlorines. Yes. Yeah. I don't know how many molecules we are getting, but just I am writing for naphthalene molecules. After that we will try to arrange the chlorines. Yes. Yeah. Now try to arrange chlorine atoms. Okay. So in dichloronaphthalene, just I am writing like this, 1,2-dichloro-naphthalene. From here, just we are fixing one position, chlorine position, and change the position of second chlorine. Here I am taking like this, 1, 3, and here just like 1, 4 position. Next chlorine here, 1 chlorine here, chlorine and chlorine, yes. Next possible positional isomers, chlorine and chlorine, like this. Okay, these are the possibilities. Next one, here I am changing position of chlorine atom here, chlorine, and another chlorine atom here. Next one, chlorine, but I am not using chlorine here. Why? Because if I are taking like this, second molecule and this molecule exactly same, second one and third one. That's why I am going to remove this one, right? Clear? 1 second. Okay. Then what is the position of chlorine? Other than this, here also not possible. Next, we are taking chlorine atom here. Next, chlorine and then chlorine. Yes, these are the possibilities, maximum possibilities. Yes. What are the possible number of positional isomers? Possible number of positional isomers: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Number of positional isomers equals to 10. 1, 2, dichloro-naphthalene. Write all possible positional isomers of dichloro-naphthalene. These are the structures. Yes, one more question. Write all possible cyclic structures of C6H12 with degree of unsaturation equals to 1. Another question. Write all possible cyclic structures of C6H12 with a degree of unsaturation 1. They are asking only cyclic structures but not acyclic structures. Okay, I am going to write the cyclic structures. What are the cyclic structures? First I am starting with cyclohexane. According to the molecular formula, what is the degree of unsaturation? 1. That is my first cyclic compound. And what is the second cyclic compound? Just I am trying to reduce the ring size, and that extra carbon atom I am writing outside the ring system. First you start with cyclohexane, and then in place of cyclohexane what we are taking? Cyclopentane, 5 carbons. That extra carbon atom I am taking here. Clear? What is another possibility? Let us try with 4-member ring system. And how many carbons left? 2 carbons. That 2 carbons you can write in the form of ethyl. Okay, right. Not only ethyl, you can write methyl and methyl also. And not only 1 position, you can change position of methyls. 1, 2 position and 1, 3 position. Are you getting idea how I am writing? Write all possible cyclic structures of C6H12 with a degree of unsaturation 1, 6-member ring, 5-member ring, 4-member ring with substitution. Okay, right. Next I am going to take 3-member ring system. Yes, 3 carbon atoms are completed. And how many carbon atoms are left? 3 carbon atoms left. 1, 2, 3. Outside the ring system. Yes. And 3-member ring system, same group you can also represent like this. This is another possibility. And here you can write in the form of methyls also. Like this. And you can change position of methyls. Methyl, methyl and methyl. And one more possibility, you can write like this, ethyl and methyl. And you can change position of ethyl and methyl. These are the maximum possibilities of cyclic structures of C6H12 with a degree of unsaturation 1. Let us count how many molecules. 1, 2, 3, 4, 5, 6, 7. Once again, let me count these molecules. 1, 2, 3, 4, 5, 6. 7, 8, 9, 10, 11 and 12. These are all possible structures of C6H12 with a degree of unsaturation 1. Okay, these are the possible structures. Next one, for example, if they are asking any type of question like what is the relation between 1 and 2 chain isomers, 1 and 3 chain isomers, 1 and 4 chain isomers. For example, if they are giving 4 and 5 positional isomers, why? Because parent chain is same. 5 and 6 positional isomers. For example, 7 and 8 parent chain is same but side chain is different. These two are said to be chain isomers. For example, if you are taking 10 and 11, what is the relation between these two? Side chain same or different? Side chain is different but parent chain is same. These two are again chain isomers. 11 and 12, what is the relation between 11 and 12? Just positional isomers. Why? Because parent chain and side chain also same. Okay, right. Next we are going for ring chain isomerism. Yes, ring chain isomerism. This one also very simple. Ring chain isomerism. First point same in ring chain isomerism. Molecular formula same or different? Yes, same molecular formula. Second one, just one molecule existing in the form of acyclic compound and one is existing in the form of cyclic compound. To explain ring chain isomerism, one condition is there. Molecule should be with double bond equivalence equals to 1. Minimum one double bond equivalence is required. Okay, let us start this example. Propene, and same thing you can write like this with the same degree of unsaturation. One is acyclic compound and one is what? Cyclic compound. Clear? For example, if you are taking butane, what is the possible cyclic compound? Yes, 4-member ring system. Not only this, you can also write like this: 1 methyl outside. What is the relation between 1 and 2, 1 and 3? What is the relation between 1 and 2? Ring chain isomers. 1 and 3 also ring chain isomers. Okay. For example, here you are taking like this triple bond. Okay. What is the degree of unsaturation? Here degree of unsaturation equals to 2. 2 pi bonds are there. And how to write cyclic compound with same degree of unsaturation? What is the degree of unsaturation of this cyclobutane? Degree of unsaturation 1. To maintain same degree of unsaturation, just I am keeping double bond. So these are the ring chain isomers. Not only that, you can also write like this: 4-member ring system. Here you can arrange the sigma bond. 2 rings are there. What is the degree of unsaturation? 1. Here what is the degree of unsaturation? Yes, degree of unsaturation 2. Okay, these are the examples for ring chain isomerism. So in case of ring chain isomerism, one is acyclic and one is what? Cyclic. One acyclic compound and one cyclic compound. Okay. This is the story about ring chain isomerism. Then we are going for metamerism, very important. Next category, metamerism. In this class, I am trying to complete up to functional isomerism. In the next video lecture, we will discuss about tautomerism. Okay, right? Metamerism. So, what is metamerism? How we identify metamers? First important point I am writing: same thing, same molecular formula. Same molecular formula. Okay, right. What is the second condition? This is a very important condition. In case of metamerism, nature of alkyl groups, nature of alkyl groups are different. Nature of alkyl groups are different around the polyvalent atom or polyvalent functional group. Very simple. Okay. Second point is very important. What is the second point? Nature of alkyl groups are different around the polyvalent atom or polyvalent functional group. Then the molecules are said to be metamers. Yes. First of all, I am trying to give these examples here, like hydrogen and halogen. Okay, hydrogen and halogen. What is the valence of these atoms? These are monovalent. With monovalent species, there is no chance for metamerism. For example, if I are taking like functional groups OH, SH, NH2, here I am taking only primary amines, 1 degree amines, but not 2 degree and 3 degree. 1 degree amines. Next, carboxylic acid and C double bond OH. For example, if acid is given like this, OH, and even in case of S double bond O, OH. Wait a minute. Yes. In case of aldehyde also, aldehyde already completed or not? Yes, completed. In case of acid halides, in case of acid amides, NH2. You observe what is the common feature of these functional groups. Here only one free valency is present. This is known as free valency. Only one free valency is there. Like that, one free valency in all these functional groups. If you are writing OH, then only that is said to be alcohol. Here also same thing, thioalcohol. Okay, like that, primary amine, acid, aldehyde, like that. So in all these groups, what are the free valencies? Only one free valency is present. This connectivity is known as free valency. That's it. Okay. Now these we are classifying. Again here also same thing, primary amide. Don't forget this condition. In case of amides, primary are 1 degree amides. 1 degree amides, but not 2 degree and 3 degree. Yes. What is the common feature of these functional groups? These are monovalent functional groups. Monovalent functional groups. Remember this point. Monovalent functional groups. Yeah. Monovalent atoms and monovalent functional groups. Here either with monovalent atoms and monovalent functional groups, metamerism is not possible. Metamerism not possible. Clear? There is no metamerism. With monovalent functional groups and monovalent atoms, there is no chance for metamerism. First important point. Second one, I am going to take polyvalent atoms like ether functional group. Okay. Here how many free valencies are there? Left and right. We can arrange the different alkyl groups. Okay, right. And here, yes. And in case of 2 degree amines, in case of, yes, 3 degree amines, and in case of C double bond O N H, yes, 2 degree amides. Next, C double bond O N, 3 degree amides. All these are polyvalent. Why? Because right side free valency is present, left side also free valency. These are known as free valencies, right? Yeah, like that. And you can use esters also. These are very important. Esters, this particular segment is taken as ester. Yes, ester. And how many valencies are there? 2 valencies are there. and you can use anhydride like this. This functional group also having two free valencies, and ketones and ester linkage like this, sulfate esters. Yeah, it has two free valencies. Okay, so what is the common point of all these functional groups? All these are polyvalent functional groups. Polyvalent functional groups. Yeah, with polyvalent functional groups metamerism is possible. Remember these 2 points. Sometimes directly they are giving which are the following molecules does not choose metamerism. So in these functional groups, because of the presence of monovalency, there is no chance for metamerism. But here polyvalent functional groups, ethers, thioethers, secondary amines but not primary. Secondary amines. Why? Because in secondary we have two free valencies. Tertiary amines, 3-degree amines. This one 2-degree amide, 3-degree amide. Next one esters, anhydrides, ketones, like that. Okay, these are the very good examples. These are known as polyvalent functional groups. Yes, by using these functional groups we are going to develop metamers. Very basic example I am taking like this, ethyl and ethyl, and here ethyl and propyl. What are the types, what type of isomerism is observed in these molecules? You observe in the first molecule, what are the alkyl groups? Ethyl, here methyl and propyl, here ethyl, methyl and propyl. Nature of alkyl groups same or different? Nature of alkyl groups are different. These two are said to be metamers. Clear? Same type of example I am taking by using sulfur like this, ethyl, and here I am taking like this. Now here again sulfur, one side ethyl group, other side I am taking propyl group. Yes, here isopropyl, and this one right side ethyl. Here simple propyl, and right side ethyl. Isopropyl, ethyl, propyl and ethyl. Nature of alkyl groups same or different? Nature of alkyl groups are different. Again these two are said to be metamers. Okay. Clear? One more example I am taking from esters like C double bond O. Here I am taking ethyl and here ethyl, ester functional group, and then C double bond O, right side I am taking propyl. Here what are the alkyl groups? Ethyl, here ethyl. Next alkyl groups, methyl and propyl. Okay, now carefully observe. In case of metamerism, around the segment we are looking for different alkyl groups. Here ethyl, and you compare with second molecule methyl propyl. These alkyl groups are different from these alkyl groups. Here ethyl, here methyl and propyl. What is the relation between these two? Metamers. They are having same molecular formula, but nature of alkyl groups are different around the polyvalent atom or polyvalent functional group. Okay, right. Next example. Anhydride also you can use like this, C double bond O, like this, ethyl and ethyl, and same anhydride. One side you can write propyl and one side methyl. These are also metamers. For example, C double bond O. Yes, aromatic ring system, right? What is the relation between these pairs? Now we know that anhydride. What is alkyl group here? Ethyl. Again here also ethyl. But here methyl. Yes. Different alkyl group. And here propyl. At least one alkyl group is different. They are said to be metamers. Now what is the relation between these two pair metamers? Come to this example. This is our ester segment. Again here ester segment. Now you look at the connectivity, which is connected to the carbonyl carbon atom phenyl. Here cyclohexane ring system. Here cyclohexane, but here phenyl. What is the meaning of constitutional isomers or structural isomers? They are having same molecular formula, but connectivities are different. Okay. Again, these two are said to be metamers. Metamers. Here phenyl connected to the carbon atom, but here cyclohexane ring is connected to the carbon atom. These two are what? Different structural isomers. And what is the classification? Metamers. Right? Is there an example for metamerism? Okay, you can take ketones also by using ketones, ethyl, and here methyl and propyl. These two are what? Metamers. So like that, any type of example is given. This is the way of identification of metamers. Metamers. Clear? Next we are going for functional isomerism. Functional isomerism. Yes, functional isomerism. What are the conditions for functional isomerism? Very simple. The name itself indicating that different types of functional groups should be present. First, molecular formula same. Molecular formula same. What is the second condition? Different functional groups. Different functional groups. Different functional groups. Same molecular formula but different functional groups. Whenever same molecular formula and different functional groups are present, those are classified under functional isomers. Yeah. Actually, in case of functional isomerism, yes, there are so many common examples like aldehydes and ketones. Okay, no problem, I am writing. Aldehydes with the same molecular formula. Aldehydes and ketones. Aldehydes and ketones. Acids and esters. Acids and esters. Cyanides and isocyanates. Isocyanates. Nitro and nitrite. Nitrite. Alcohol and alcohols and ethers. Okay, these are the some common examples for functional isomers. For example, if you are taking aldehyde like this, C double bond OH, and same thing you can write like this, ketone. What is the relation between these two functional isomers? Acids and esters. Any acid you select like this, C double bond OH. Okay, and if you want to write ester with 3 carbon atoms, you can write like this. Acid and ester also say functional isomers. Cyanides and isocyanates, triple bond N, and here nitrogen, triple bond C. One second. Here one coordinate covalent bond is present. Now I am not going to discuss anything about bonding nature. Just I want to put like this, NC. That's it. 1, 2, 3 carbon atoms. 1, 2 carbon atoms. Yes. Okay. Yeah, numbering also not required, no problem. Cyanides and isocyanates. What is the relation between these two functional isomers? Next one, nitro. Simply I am writing like this, NO2, and here ONO. These are the functional isomers. Alcohols and ethers. Alcohols and ethers like hydroxy group. Here you can write ether with 3 carbon atoms. These are the common examples for, very common examples, routine examples for functional isomers. But I am giving high priority especially in 3 cases. Very, very important. Most of the time we are getting confusion in these three cases whenever we are dealing with functional isomerism. So I want to give high priority for 1 degree amines, 1 degree amines, 2 degree amines, 3 degree amines, 3 degree amines. 1 degree, 2 degree, 3 degree amines are considered as different functional groups. Different functional groups. Like that, normal alcohols and phenols with same molecular formula, again considered as different functional groups. Different functional groups. Come to third one, primary amides, acid amides. Primary amides, secondary amides, tertiary amides. These are also considered as different functional groups. Very important. In functional isomerism, mainly we are getting confusion from these three. There is no problem with other functional groups. Now whenever primary amines, secondary amines and tertiary amines, 1 degree amines, 2 degree amines and 3 degree amines are given with the same molecular formula, they are considered as different functional groups. Like that, alcohols and phenols, different functional groups. Primary amides, 2 degree amides, 3 degree amides, these are also considered as different functional groups. Let us start some simple examples. Here I am taking benzyl alcohol CH2OH, second one here OH and methyl. Next, benzyl alcohol, here they can give like this OH and methyl. For example, same benzyl alcohol OH methyl group, they can give like this at fourth position. What is the problem? At any position you can take. And another example, yeah, aromatic ring system, right side, some 6-member ring is given, here OH is given, and here methyl group, same OH I am taking here. Not only that, you can take one more example like this ethyl group and OH. Like this, okay? Now you observe this is not the phenol. Simple, this is what alcohol and this one phenol. What is the relation between these two? These two are said to be functional isomers. Functional isomers. Same thing, alcohol and phenol, functional isomerism. Functional isomerism, okay? Right? Here also same thing, functional isomerism and functional isomerism. Very important examples. Whenever there is simple alcohol and phenols are what given, what is the relation between both pairs? Functional isomers. Yes, I am giving like this with 3 carbon atoms with NH2. Yes, no problem. NHCH3, nitrogen, methyl. I am using same molecular formula. What is the degree of this amine? 1 degree amine. 1 degree amine. And this one 2 degree amine. Next, 3 degree amine. They can give like this 1, 2 and 3. They can select either 1 and 2, 1 and 3, 2 and 3, 2 and 3. What is the relation between 1 and 2? Yes, these two are functional isomers. 1 and 3 also functional isomers. 2 and 3 also functional isomers. Okay? Why? Because already we know that 1 degree, 2 degree and 3 degree amines are considered as different functional groups. 1 and 2, 1 and 3, 2 and 3, they are said to be functional isomers. Like that, you can take amides also like this 2, 3, 4. Yes, I am taking like this NH2. Here my wish, I am taking 1, 2, 3, 4, 5 carbon atoms. Yeah, okay. Come to the second molecule. Here I am changing degree of nitrogen. Yes. And how many carbon atoms left? 4 carbon atoms. I am taking here 3 carbon atoms, here 1 carbon atom. No problem. Here what is the degree? 1 degree. And here 2 degree. Next, C double bond O N. Arrange methane and methane. 1, 2, 3, 4, 5. This is the 3 degree amine. Okay. 1 second. 1, 2 and 3. Same thing. 1 and 2. 1 and 3. 2 and 3. What is the relation? Yes, these two are said to be functional isomers. Again, functional isomers. 2 and 3 also functional isomers. Functional isomers or functional isomerism, right? This is a story about chain isomerism, positional isomerism, ring chain isomerism, metamerism and functional isomerism. Okay. And finally, I want to tell one important point that for example, if there is a functional isomerism and metamerism in single option, functional isomerism and metamerism, high priority given to functional isomerism. So note this point. First point, in presence of functional isomerism, neglect metamerism, chain isomerism and positional isomerism. These 3 we are neglecting. Okay. In presence of functional isomerism, neglect meta, chain isomerism and positional isomerism. Second point, in presence of metamerism, neglect chain isomerism and positional isomerism. Okay. In presence of functional isomerism, neglect meta, chain and positional isomerism. In presence of metamerism, neglect chain isomerism and positional isomerism. These are the very important points in structural isomerism. So today we covered chain, positional isomerism, ring chain, metamerism and functional isomerism. In the next class, we are going to make a great video on tautomerism. That's very lengthy topic and very important for mains and advanced. Okay. Thank you.